Out to Chase Berry for three. Rebound by Peyton Crispin. He's going to put it back. And
they got it!
The Lakers hit a three.
Welcome back again. Music Court, home of your SWOCC Lakers.
Can't get the shot to go, and the Lakers win the ball game. Go! Lakers win! Lakers win! Lakers win in overtime. 108-106.
Congratulations, you just got accepted into college. Now, how do you pay for it? Fortunately, there are several options out there to consider. Follow this simple step-by-step guide as you figure out how to pay for college. Step 1, fill out your FAFSA? Free Application for Federal Student Aid, FAFSA. Your FAFSA will determine if you qualify for financial aid, including grants, some scholarships, work-study, and federal student loans. The good news is, most people qualify for some financial aid, which is why this is the most important step in figuring out how to pay for college. Step 2. Figure out how much you may need to borrow by weighing your college costs versus your contributions, including any grants or scholarships. Some easy arithmetic will make your math teachers proud. Let's say your college of choice costs $30,000 a year after factoring in tuition, housing, books, lab fees, and a laptop. Now, let's pretend that the money found in your family swear jar, your bowling scholarship, your federal grant, and the money you saved as a scuba instructor contributes $10,000 to your college fund. Voila! This is how much you will need to cover through other means. Many families consider student loans a reliable option. Step 3. There are two categories of student loans you can consider, federal and private. Federal loans are made by the government and private loans are made by private lenders. In some cases, families use both to cover the cost of college. Compare student loan options by looking at their interest rates, repayment options, and fees. Interest rates vary depending on the loan type. Federal loan rates are fixed, while private loan rates can be fixed or variable and are determined by your credit quality. Adding a cosigner, like mom and dad, may help lower your interest rate. Repayment options for federal and private loans are also different. Some providers require in-school payments, some don't. Take a look at these now and choose an option that makes sense for you. Watch out for fees. Fees can be charged upfront or in repayment, and they add to the total cost of the loan, so you end up paying more back. Step 4. Factor in other benefits when researching a loan. Some reduce your interest rate and some give you cash back. For example, Discover student loans have no fees and give you a cash reward for a 3.0 GPA or equivalent. Let's go through these steps one more time, just in case you needed a refresher. Step 1, fill out your FAFSA. Step 2, weigh your school cost versus your contributions. Maximize any free money like personal savings, grants, and scholarships before considering loans. Step 3, compare interest rates, repayment options, and fees. Step 4, take into account any benefits the loan provider may offer. Don't forget that you can continue to reduce the amount you need to borrow with scholarships. If you are an eligible current or college-bound student, you can enter to win a $2,500 Discover Student Loan Scholarship Award. Head over to collegecovered.com to learn more about paying for college and enter to win. No purchase or loan required. The first week of school can always be a bit overwhelming, but a little bit of good old college ingenuity can go a long way. Here are 10 collegiate quality hacks that will make campus life a little more comfortable.
Do you like to work with metal, fire, electricity? Would you like to make money doing it? At Southwestern, we can help make your dream a reality. With our degree and certificate programs in welding, you'll be prepared for a career in the welding and fabrication industry in as little as a year. Check out our website and let Southwestern spark your career in welding today.
I'm Private First Class Taylor Irwin, and I'm with the Maryland Army National Guard. I joined the Army National Guard to begin my career. I have been awarded tuition assistance, and I picked furthering my education. Right now we're just going through the basics. We're doing the confidence course. It's to get over your fears basically and to see how far your team has come. It takes a strong leader and strong drill sergeants as well. You're gonna meet some really cool people and they're going to help you get through it either way. So it's going to be really fun.
This is Southwestern's dental assisting program. In just one short year, you could be a dental assistant. Sign up now for your one-year dental assisting certification.
Well, welcome everybody, and thanks for coming out to the Physics and Astronomy Lecture Series for December 1st. I have the pleasure of introducing a friend of mine and also a colleague at the Oregon, or through the Oregon Space Grant Consortium. That's interesting project that Mr. Greenberg and his students are currently working on. To launch a CubeSat into space and to do a lot of interesting science, but I will let Andrew take care of all the science stuff. Please join me in welcoming Andrew Greenberg.
Hi. Well, usually I run around the stage and everything, but they told me I have to be right here. So I'm going to sit here and be really boring. I'm sorry. Also, there's not a lot of people in the audience, which is kind of cool because it means that we can actually talk and I don't have to ignore you. If you have questions, feel free to raise your hand and yell at me, and maybe I can answer right in the middle. But what I am going to do is I'm going to fly through these slides. Like I have 600,000 slides, and we have an hour. And at 100 slides a minute, I think 10,000 slides a minute. I'll probably blow through most of them, so you can, at the end, you can go ahead and ask me questions as well. Well, thank you. I appreciate that. All right. So, hi, I'm Andrew. I'm adjunct faculty in electrical and computer engineering at Portland State. That means I'm a fake professor, unlike Aaron, who's a real professor. I help with this project, the OreSat project, which is primarily run out of Portland State, but is statewide. And we have quite the agenda tonight. I only have an hour, but I have 6 years of work to talk about tonight. So the first is sort of the introduction to space and building your own satellite, because you really ought to build your own satellite too. It's 2018, everybody should have a personal satellite. And then I'll talk about our project and go from there. The first thing you need to ask is, we all talk about space and satellites in space and rockets in space and things like that, but what is space? And that's a really good question, because there's there's no good definition to some extent. Here is the atmosphere down there. You see the mountains. Oh, wait, I have a little red thing. Ooh, look at my red thing. Down here we have mountains, and we have jet planes at 10 kilometers, and we go up and we go into the mesosphere and the stratosphere. And then at one point we say, well, this space. Well, not really. The atmosphere keeps going. It keeps going for thousands of kilometers. It's just really, really rare. But our friend, Professor Dr. von Karman, one of my favorite people, said, well, let's just arbitrarily say 100 kilometers, because that seems about right. And it turns out that, and I'll tell you more about this in a minute, your plane has to be in orbit if it needs to fly on the atmosphere, using its wings at that altitude. So everyone thought, okay, space, 100 kilometers. Under that, not space. All right, sure. So that's not very far, really, when you think about it. Like if you took Portland and you headed south, we'd pass Salem, but we wouldn't make it to Eugene, right? So this 100 kilometers is not far. In fact, it is disturbingly thin to get to space. We have just this very thin shell of an atmosphere around the damn planet, and we should all be very, very concerned about that it's like only 100 kilometers. The International Space Station's at 400 kilometers. They need to get out of the atmosphere so they can go around the planet. But here's the real question, which is, how do I go to space? And how do I stand in space? Because if you take a tennis ball and you throw a tennis ball, what happens? It comes down, right? Now, if I throw a tennis ball up and it goes to the altitude of the moon, what happens to the tennis ball? The answer is it falls down. It falls down that thing. This is a gravity well. We live at the bottom of an infinite gravity well, which when you throw something up, it comes down. If you throw it fast enough, it turns out there's something called escape velocity, and then it can go forever. But the gravity really does go on for an infinite distance. So how do you stay in space? How is the International Space Station in space? When you actually graph it, as it sort of is, it is a disturbingly deep gravity well. All right, so that was weird. All right, blank slide. So Newton came up with a really good idea. He said, well, I'm going to go climb to a mountain at the North Pole, and I'm going to fire a cannonball, and it's going to go really fast, and the cannonball is going to go out, and then it's going to, Earth's gravity will attract it, right? And so the cannonball will go straight out, and then it will eventually fall down and hit the ground. And what you notice is when it does this, it sort of goes off to the side, right? It's kind of going off this way, and then it hits the ground sometime down there. Well, what happens if you fire it really, really, really quickly? The answer is, by the time it hits the ground, it hits you in the back of the head. And this is orbit. This is going so fast that by the time you fall down to the Earth, you've already gone around it once. And not many people realize that, right? They think you go up in space and you hang out and there's zero gravity. Oh, no, no, no. There's tons of gravity in space. It's just that you're whipping around the planet fast enough so that you actually stay up in orbit. It's just like those annoying little coin wells. You put the coin in and the coin goes around and then falls in the middle, except there's really no friction, so you keep going along around and around. So that said, the problem with that is you have to go really fast. So 8 kilometers a second is 17,000 miles per hour. It turns out that's really, really, really fast. And if you wanted to just get a Coke can into orbit, which is about 1 kilogram, you need about 30 megajoules. 30 megajoules is like 8 kilograms of TNT. And so think about that. With a single Coke can, you could take out, what is this, a city block with that much kinetic energy, right? So going up is 10%. That's hard, but not terrible. Going 90% of the energetic way there, going around in orbit, that's hard. That's why rockets are really, really big and mostly fuel, because of that speed. Going up, meh. Going around, okay, hard. So there's different kinds of orbits once you get up there. Low Earth orbit is what we're used to, because that's where the space shuttle went. That's where the International Space Station is. You can keep going out farther, where the GPS satellites are in medium Earth orbit. And then you can go way, 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 way out to geostationary orbit, which is a very special kind of orbit. And that's because it takes 1 day to go all the way around the planet. And of course, if you take 1 day to go around the planet, then you go around as the Earth rotates, and it looks like you're just standing, you're just suspended above the Earth but you're not. You're actually rotating with it. That's why there's a lot of stuff in geostationary orbit. There's other kinds of orbits that you don't need to know about. The orbit of the moon, of course, has an orbital period of 27 days because it's very far away. So here's kind of a scale for that. Off to the left is low Earth orbit. That's kind of in here. You know, we're like down here for the International Space Station. And then you start going out, and most of the junk they talk about is down here in low Earth orbit. And then we can keep going, and now you see we've zoomed way out. And geostationary, I believe, is here. And then way, way, way out here, we've got the moon. So we're all in the same gravity well. The moon is in the gravity well of the Earth, right? We're just orbiting around the planet really, really, really fast. All right, so when you talk about orbits, there's lots of ways you can describe orbits. We're not going to go into it. I threw up some fancy things. We can talk about apogee, how far away it is, or perigee, how close it gets, blah, 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 whatever. We can describe orbits because it's all mathematics, right? It's two bodies and a gravity well. We understand how those move, thanks to Newton. You often see these. They're called ground tracks. There's this funny line. If you smushed the square Earth on this map into a sphere, what you'd see is a ring around that funny sinusoidal shape makes a ring. And so that's why when you see this, think, oh, it's in an orbit, and the top of the ring goes up to, in this case, it's the ISS, so about 50 degrees right above Oregon, and then all the way down to tip of South America. So there you go. You're now an expert on orbits, right? Congratulations. You've passed Orbit 101. Let's talk about satellites. So this is my favorite thing because this is no satellite in the history of satellites ever looked like this, but it's great because it's got all the things in it. So what's in a satellite? Well, you got to power it, right? Well, how are you going to power it? If you've got batteries, they're going to run out. So you use solar power. And even in the 1950s, we had solar-powered satellites. They were the very first solar-powered things, actually. And so we have solar panels here, and we have batteries to store it. So when you go into the night behind the Earth, you can still run your satellite. You have radios and transmitters and antennas. Some of them have little rocket motors. Most don't. It turns out that once you get to where you're going in orbit, you don't need motors anymore. You can just kind of go around the planet. And then, of course, cameras and other science payloads. So how about a real satellite? Well, here's one of the early microsatellites from the late 90s, I believe. And it's got the same thing. It's got solar panels and a battery pack and what they call a bus, which is kind of all the guts, the stuff that makes the satellite work. And then antennas down here, and this one has a little rocket motor as well, and blah, blah, blah. So, you know, power, computers, sensors. That's a satellite. Congratulations, you now know all about satellites. Two other things you should know is that in the satellite world, we tend to separate out what's called the bus and the payload. So the bus, from the early computer bus days, is the sort of interior guts of the satellite that no one really cares about. It's the satellite, it's the solar panels and the batteries and the mission computer and all the things to make the satellite work. The payload, literally payload, is the thing that we all pay for when they set up a satellite. So that's Earth observation or science or astronomy or, of course, we know telecommunications, all that kind of stuff. So, and GPS satellites are really just fancy atomic clocks with antennas on them. And so if you really want to talk about what a GPS is, and you can ask me afterwards, it's just an atomic clock. It's kind of cool. So satellites are great, but they're really expensive. They cost hundreds of millions of dollars. But it turns out there was this guy. His name is Bob, and Bob Twiggs was down at Stanford. And Bob was getting angry because in his space science courses, he couldn't actually get the students to launch their own satellites. So he thought, well, you know, this is the wrong thing. We don't want to build these really big satellites. Can we build little tiny satellites? And can we have the students build little tiny satellites and launch them? And so he came up with the idea of the CubeSat. Now, that one thing over there is called a 1U CubeSat. It's 10 by 10 by 10 centimeters. We like to say it's a cubic liter, which is why he chose it. No, Bob didn't choose that size because of that. He chose it because it's the size of a Beanie Baby box, which is sad. So this is a 1U CubeSat. That's how big it is. And there are hundreds of these in orbit around the planet right now. And they've got everything a little tiny satellite needs. But you can also make them bigger. I'm going to talk about a 2U cube satellite called Earth. And you can go up to 6U or even 12U, although those are not quite as useful because they're big. And there's all sorts of design parameters for this. If you're going to build your own CubeSat, you just do a Google search for CubeSat dimensions, and you can build your own CubeSat. So these are some real CubeSats. Off to the left is a 1U, and then a 2U, and then a 3U, and then a 6U. And these are all before they were launched, obviously. And you can also see 1U over there. And the cool part is, inside this little tiny box, inside this little Beanie Baby box, hey Bob, is everything you'd expect in a satellite. We've got solar panels, that's what these things are. We've got battery packs on the inside. We've got a little flight computer. We've got radios. We've got antennas up here. It's a teeny tiny little satellite. So, and it turns out that this was nice that Bob came up with this sort of form factor, like a shipping container, if you will, right, for satellites. It's a standard form factor. But it turns out that's not the really important thing. The really important thing is that nobody's going to let an undergraduate student build a satellite and put it on a $100 million rocket with a $100 million satellite, unless you put it in a box. And if you put it in a box, and if that CubeSat explodes and catches fire and goes into shrapnel and gets shaken into little tiny bits, that's fine, because the box is closed until the $100 million satellite is off and in space, and then they open up the little box, and the shards and flame from the small satellite come out, and that's fine. So it turns out it's all about risk. And so by putting them in these what are called P-pods, the Polytechnic Picosatellite Orbital Deployer, thank you guys, you can take these CubeSats, put them in there, and then you can put them anywhere on the rocket, and they're safe. They're safe because they're in a box, and you don't care what happens to them. And in fact, they do terrible things to us, people who make CubeSats. They put them at the bottom of the rocket, right by the engines. There's terrible vibrations and heat and all sorts of terrible things, and they don't care because they're in a box. So, but that's great. What happened, interestingly enough, is when that happened, all of a sudden, it became really easy to get into space. Oh, by the way, the ISS also has an orbital deployer. So there's the ISS, and there's a couple of 3U CubeSats being hucked off the International Space Station. It's actually kind of cool. All right. So this was meant for undergraduate and graduate students to build their own satellites, like you guys, right? It turns out that other people were interested in little teeny tiny satellites as well. And now most satellites in orbit are actually commercial. This is from Planet Labs. It's a Dove. They orbit around the planet, and there's, I think, 200 or 300 of them right now. And they take a picture. They actually image the planet at 10 a.m. local time every single day, every part of the planet. It's really cool. And it's really funny because that's not something you see every day. They have so many satellites that they can't store them anywhere, so they started piling them on top of each other. So that is a pile of satellites on Planet Labs' table, which is great. And congratulations to us. The first interplanetary CubeSats last week successfully fulfilled their missions. If you guys saw the InSight lander land, you saw it or you heard it land live via the Marco satellites. So these guys, this is a 6U CubeSat. This is a 6U CubeSat with the solar panels and a big, basically, antenna deployed. So yay, first interplanetary CubeSats were a success. All right. Yeah, yes. So now you know about satellites, you know about CubeSats, you know a little bit about space. There's problems. Space is hard. And we like to say that space sucks, and for the appropriate reason that it is a vacuum. And there are all sorts of problems with what you're about to do. So you're going to make your satellite. What do you have to be afraid of? You really have to be afraid of essentially everything. But one of the worst parts is going to a vacuum. If you have plastic, it tends to outgas. As it outgasses, the little volatile organic compounds kind of come out, and then they tend to cluster around your satellite, and then they tend to go and they stay on your lenses, so all your lenses start to fog up. Worse, if you have two pieces of metal, say 2 pieces of iron, and they're really, really clean, and you touch them in space, it turns out that there's nothing to tell the electrons in the metal that they're not part of the other chunk. And so when you push them together, it turns out you no longer have 2 chunks of metal, you've got 1 chunk of metal. And that's called vacuum welding. And it's not as terrible as you might think, but it is a problem. If you have two metal things moving against each other, you have to deal with it. And then finally, you can get trapped air bubbles that expand out. And in a minute, I'll tell you about something that's really terrible. And this is really why vacuum is a problem: thermal. So we're used to a hot cup of coffee going cold. When you have a hot piece of your satellite, like an amplifier or a power supply, there's nothing to cool it off. Yes, it will radiate into space, but very, very, very slowly. And so this is the real problem of a vacuum, is there's no cooling, which is interesting. And then it turns out there's other terrible parts about cooling, right? So you're in space. On one hand, you've got a 5,800 degree Kelvin star that's a U or two away, that's baking your satellite on one end. And on your other end of your satellite, you've got, 2.7 degrees Kelvin from deep space. And so you can actually have minus 90 degrees C on one side of your satellite and 120 degrees C on the other. So that's like, 200 plus degrees C across your satellite. So heat is kind of flowing through your satellite. So this turns out to be really, really terrible for everything that's on a satellite. Like computers hate this. It's kind of hard to see. This is an orbital simulation of OreSat, of what we did. And we were like, so what happens if you threw just a chunk of aluminum into space? What would happen? And it turns out if it's not actually spinning, that's very, very, very bad, because it gets very, very hot. And if it's spinning, well, okay, that's fine. It's not so bad. It's only at like minus 20 degrees C. So it's hard. Space is hard. And worse, you've got all these computers and electronics on board, and you want those to control your satellite, right? Well, it turns out they don't always do that, because there's radiation in space, and computers in particular really don't like radiation. What happens is, you've all heard of bits in your computer. Well, what will happen is stray radiation will come in, hit your chip, turn into a cascade of particles, and start flipping your bits. So when you thought you had a 1 or a 0, you now have the opposite. And that's called a single event upset, and you have to deal with that all the time. In fact, you can't trust anything, because it actually could be just, your bit that says destroy the satellite now could be a bit flip rather than the actual command to destroy the satellite now. So this is a real problem, and you end up doing things where you've got two computers in parallel doing the same kind of task. And there's other stuff we could go into. The really thing that we really will make us cry is called single event burnout, where no matter what you do, you've got a high energy particle coming in, and it just takes out your chip, and there's nothing you can do about it. So we talk about defensive design a lot. Luckily, in low Earth orbit, it's not very bad. The Van Allen belts are away from us, and so we're kind of coddled in low Earth orbit, so we don't have to worry too much about it. And then finally, we got to power this. But it turns out that, of course, the only way we can do this is using solar panels. Solar panels are not a great source of power, and they're really big, and they don't like them flapping in the breeze when you're on a rocket, so you have to fold them up and then to deploy them. And also, by the way, when you're running on solar, it turns out you don't get solar 50% of the time, because the planet's in the way, unless you're in a very special orbit. And so solar's okay, but it's not great. We really like radioisotope thermoelectric generators. Those are great, but of course, no one likes plutonium. So, and then finally, once you're in space, it turns out no one's going to hit the reset button on your satellite. Once you're deployed, you're done. That's it. And so if you screw up and you send the wrong kind of software up to your satellite and it doesn't reboot after you reprogram it, your satellite's done. And so the whole idea of a remote operation is everyone has this problem who does remote sensing. It's particularly bad in space, because not only do you have to upload your new firmware, and not only do you have to reset your computer all the time, but you've also got all this radiation that's desperately trying to destroy all of the software you've got in memory at the same time. And we only get to debug through a slow radio. And so a lot of the things that we'll be doing over the next couple of years with Oregon's first satellite is testing, integration testing, what we call day in the life testing, making sure it does the right thing over and over and over again. So congratulations. You are now ready to build your own satellite. We'll meet tomorrow at, now that you understand the context for satellites, let me tell you a little bit about the one that we're building. So we have a bunch of space nerds at Portland State. It's a student club called the Portland State Aerospace Society. It's not just the students. it's also faculty members, and it's people from local industry who come in and mentor the students. And that actually turns out to be a really good thing. It's one of the reasons we've been around for a really, really long time. We're a 501c3, and everything that we've ever done, including the rocket you see there and the satellite that we're working on now, is open source. And open source means that all the CAD data, all the software, everything you need to run it has been published to the web. So we've been doing this for a while. We've got some silly firsts. We were the first to run Linux on a rocket. We were the first to push Wi-Fi past Mach 1. And there's some of the, over here you can see a rocket, controlling itself. And over here is slow motion launch from Central Oregon, actually, outside Bend. So these are amateur rockets that we build at Portland State. So one of the things that makes us special, actually, is that we don't just build the rocket part of this. And we've had a lot of different rocket launches. We've had 14 so far. Not all successful. A lot of engineering education, as you all know, is failure. And so it's actually much more interesting for the rockets to fail than it is to succeed. But of course, we all cry when they fail. So we do something that's kind of special for amateur rocketry. We don't just build the rockets. We build computers that go inside the rockets and control the rockets as they fly. And you know, we have all sorts of cool things on board the rockets. We have cameras and sensors and control things and blah, blah, blah. None of which is, it's all terribly interesting, but I won't talk about it tonight. But we did something funny, which is, you know, when we realized we built all this computers and electronics for a rocket, we thought, oh, you know what we did? We actually built a nanosat. We bought a CubeSat, but it's the wrong shape. It's cylindrical instead of cubic. So maybe we should build a CubeSat. So it turns out that NASA has this program that you should all know about called the CubeSat Launch Initiative. And if you write a proposal and it's good enough and NASA agrees that it's worth funding, they will launch your CubeSat to space. It doesn't fund your CubeSat, but it gives you a free ride to space. And so we applied in November 2016 with OreSat, Oregon's first nanosatellite. And we didn't think we were going to get in, and so we put all sorts of really great phrases, and we had a really good time with it. And we really, like, you know, it was a good excuse to put together a proposal so that we kind of understood what it was like to do this. And then we thought, okay, we'll do this once, and then we'll start working on it, and we'll get in maybe next year. Oh, no, they let us in. So after panicking for a little while, realizing that they let us in, we reached out to people and started actually building the satellite. So it's not just PSU. It's also University of Oregon, who's providing the payload, Oregon State University through the Space Grant Consortium, who's helping us out, as well as the School of Engineering. And Lane Benton Community College is working on it one small part, and we hope SWOCC as well. And we've been talking to Aaron actually about having some participation in the next year, which would be really cool. So we got in. So it turns out we have to build a CubeSat. And so that's what we're going to build. It's called OreSat. It's a 2U CubeSat. Just to give you some sense of scale, this is the first prototype of OreSat made out of aluminum. And it's this big. It's not very big. We call it a loaf of bread, and it's about right. So we're actually really pleased that we've made as much progress as we have so far. You should probably know what it does. So the first thing is the one that we're most excited about, and that I think has the largest impact on the state of Oregon. We all love the Oregon eclipse. It was a chance for us to get together as a state and do something cool in science, and so we want to follow on the heels and do something cool for the state of Oregon. So this is the most ridiculous thing you've ever heard, but it's really cool. So we're going to have high school students build a ground station. And yes, apparently they need to wear hard hats while they build a ground station. Okay. And it's a little handheld thing. It's going to be something that you can point up at the sky. And then they're going to go to our website and ask for a pass. They're going to tell us what their latitude and longitude in Oregon is. And as OreSat goes overhead, we're going to point the satellite down at their location in Oregon, turn on a video camera, and start broadcasting live video from space. They're going to point at the satellite, and you'll get some kind of large thing. They won't be seeing themselves live, but they'll see their area of Oregon live, and they'll be able to download it live from space. So this is a huge STEM outreach for the state of Oregon. We call it the 400-kilometer selfie stick. But it's really about the STEM outreach to the high schools. So they'll be learning about orbits, they'll be learning about satellites, they'll be learning about all the things you might want them to learn about when you talk about space and STEM and things like that. So we're very excited about this. We hope to be in every high school in Oregon. We need high school students and we need teachers and physics teachers. It's going to be part of Physics First freshman year, we hope, thanks to the University of Oregon and Dean Walton, who's helped us, what's it called, crosswalk it to the curriculum, which is great. So it's not just the $50 ground station or less. You can build it from scratch for almost nothing, actually. It's also, you can build a little tiny version of OreSat that's a 1U CubeSat. And that little teeny tiny 1U CubeSat, we're calling a mini OreSat, you can fly that on a high altitude balloon. And with a Raspberry Pi camera and a single board computer and a GPS and a battery pack, you can make your own teeny tiny satellite and fly it at 100,000 feet on a balloon and use your ground station that you've already built for OreSat on the balloon and get live video from your balloon. Not only do we have the STEM outreach mission, but we also have a science mission. We thought it was important to do both. So we talked to the University of Oregon, and they actually came up with a really, really awesome and interesting, and for us, very doable science mission. So it turns out that there are clouds very, very high in the sky at about 10 to 20 kilometers called high-altitude cirrus clouds. And these high-altitude cirrus clouds have a really interesting property, which is they reflect infrared radiation, excuse me. So the sun hits the ground, the IR goes back out, gets reflected back by the high-altitude cirrus clouds, and then warms up our dog, apparently. I don't know why we have a dog, but we do. So what we're going to do, and by the way, these cirrus clouds, very, very difficult to see optically and through other kind of wavelengths. So there's no one satellite up there right now that really shows or can show the global distribution of high-altitude cirrus clouds. So they're building, University of Oregon has developed a camera system that, camera system that looks at the reflected sunlight from the high-altitude cirrus clouds. It turns out these tiny little ice crystals in the cirrus clouds are like mirrors, and so they reflect the entire solar spectrum. So we should see the entire spectrum with no absorption lines. Clouds, on the other hand, have water vapor in them, or water droplets, and those absorb certain bands of the solar spectrum, so we won't get the whole solar spectrum. So we're looking at different kinds of spectrum being reflected, and we'll be able to see if there's high-altitude cirrus clouds. Not only can we do that, but it turns out absorption does the same thing, so high school students will also be able to build a handheld ground station for the Cirrus Flux camera so that they can be doing from the ground measurements up while we're doing from space measurements down. So here's some, you've seen these in the sky sometimes when they're visible. These are the cirrus clouds, and they're way, way, way up there. So this is pretty great. We only need 5 cell phone cameras and some filters and things like that to take a look at that, so that works very well for us. And here's their prototype that they built and one of their first computer classifications of what they saw above. And like I alluded to before, it's not just us. We hope that Oregon high school students as well will build Cirrus Flux cameras and aim it from the ground, take a look up, and do what we call ground truthing, making sure that the things that we're seeing on the satellite are also high-altitude cirrus clouds. And it should be relatively cheap, like $100 or so. And then what happens when you get a bunch of open source space hipsters really excited about building their own CubeSat? They make an open source CubeSat. And so a huge part of our mission is building a CubeSat that other people can build as well and build on top, so that when we do future missions, all of the technology that we're pioneering will have been improved by other groups, which we're really excited about. So everything we do is online. So if you want to go build your own OreSat, please do. There's the link to GitHub where we actually publish everything. We have everything under the CERN Open Hardware License Agreement and the GNU GPL, which are 2 license agreements. It's kind of funny because other groups are already asking us about our designs, which is bad. We tell them, no, don't use our design until after they've flown, because we don't want to catch fire in space. Let's make sure these things work first. LibreSpace Foundation was the first group to actually do an open source satellite, and that's in orbit right now. So remember a bus, a satellite bus? That's the internal guts of the satellite. So we have two payloads, right? OreSat Live, the video from space is one payload. The Cirrus Flux Cam, that's the other payload. And so this is the OreSat bus. And for those of you who are around in the mainframe days of the 70s and 80s, we have basically a card cage bus. So if you come up later and take a look at the prototype, what you'll see inside are these little cards that slide in. And it turns out this is really important because when you have lots and lots and lots of undergraduate students working on things, you never want them to all be working on the same thing. So everyone's got their own card, essentially. And so you see some antennas up here and antennas down here, some RF connections on the back plane where these cards slide in. These are the reaction wheels we'll talk about in a second, and then the solar panels on the outside. And if you explode that, you can see the very easy to machine aluminum outsides and the back plane and the cards I was talking about and the solar panels. So it's a very simple setup. And it's very important because when you work with lots of modular teams, they all need one way to talk to each other, and that's through that backplane, through that card slot. So I could go into incredible depth on all the exciting, really technical things, and I won't. But this is the block diagram for OreSat. On the left, you can see the full block diagram, and in the right, you can see the little bits, and it, you know, the 2.4 gigahertz antenna, the N card, our Wi-Fi, our star tracker, blah, 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 blah. It goes through here. It looks very professional and very impressive. But this is the actually ugly truth, which is everything that we do is on whiteboards, and it changes every month because as we learn about what we're doing, things change. I love the phrase, building the airplane while you fly it. This is very much like that. When you do your first engineering project in an area you've never done before, you end up changing and doing things and being agile and changing things on the fly, which is great. But that's fine. That's why we learn. So OreSat is being powered by solar panels. We're the first to fly these little guys. These are chemical vapor deposition gallium arsenide solar cells. They're very, very, very thin. They're like 100 microns thin. They're flexible. I can actually flex this one. And they produce 2.8 watts of power when we're in full sun. That's the entire array. That's all 8 of ours will produce 2.8 watts. So we basically have a USB charger plug-in to power our satellite, but only 50% of the time because our orbit really only gets sun 50% of the time. So a lot of what we're doing inside the satellite is to make sure that we've got enough power savings to be able to run off this really, really weak supply. One of the things that helps us is Moore's Law and modern technology, right? So who was around for a Windows 98 computer? Yeah, okay, a lot of you actually. So your Windows 98 computer is now that. So that's an Octavo 1 gigahertz ARM Cortex processor that would put your Windows 98 laptop or computer to shame. And you can see the comparisons on the bottom. This is the Pentium 3, this giant thing over here, and this is about twice as much computational horsepower. We've got way more RAM, we're going to have way more flash on board, and we're 1/20th of the power. So again, we talk about CubeSats and microsatellites. We weren't able to do this 20 years ago. This really is the last 5 to 10 years these things have really kicked in, which is exciting. So one of the questions that you should be asking yourself is, so we're going to beam live video from space, right? So how are you going to beam live video from space? Well, we came up with the worst idea in their history of worst ideas that make other people sad. Is there anybody here who works in satellites? Excellent, that was the right answer. Because they would be laughing right now, and I could identify you, because we're going to use Wi-Fi. So you can't get Wi-Fi from your basement, but we can get Wi-Fi from space. And the way that we're doing that is we're amplifying the signal, obviously, and we're using very, very high gain antennas. And so we have a 10-watt power amplifier. Well, you've got about a milliwatt of power. So we've got about 10,000 times the amount of power, which is still not a lot, but it's enough to get down to the ground. And high altitude high gain antennas. The reason we chose Wi-Fi is it's so cheap. Instead of having kids build their own very complicated radios and tune them, which is very difficult, or buy very expensive space radios that cost literally $5,000 a pop, that board is about $8 from Amazon. All right, space radios it is. Now, technically, we are not the first people to do Wi-Fi from space, I'm sad to say. It turns out that NASA totally cheated and flew Wi-Fi from space, but they had a 7-meter dish, all right? That's a 20-foot diameter dish, so they totally cheated. So anyway, so we like to think we're still the first people. So this is some testing we did on a light airplane. You can see the airplane over here. That's the antenna from the satellite and the tracking that we did from basically, we were down here in Portland, and we watched it go from Vancouver to near Mount Rainier. Sorry, not Mount Rainier, Mount St. Helens. And this is the ground station down below. So we're using Wi-Fi from space. The other thing that we need is a GPS receiver. We need to know where the satellite is. So we're building our own GPS receiver. Yes, GPS will work in space. No, your regular GPS receiver won't do it because the GPS receivers will shut down if they think they're going more than 1,000 miles per hour. So we're building our own GPS receiver. And if you ever want to have your brain really, really hurt, work on GPS. It's the only time you have to combine the general theory of relativity, digital signal processing, radio frequency engineering, embedded systems. Everything that's hard in engineering is jammed into GPS. It's kind of amazing. So we have lots of very unhappy students right now working on this, which is adorable. So when you work on something new, things bite you in the butt, and you think, oh, I didn't expect this, right? Sometimes you're pleasantly surprised. We thought that one of the hardest things for us to do was going to be to determine which way the satellite was pointing. And it turns out you do that with something called a star tracker. It's just a camera. The camera points and looks at the stars, and it looks at a big database of stars and says, my camera's pointing this way. That's a star tracker. Well, we were all ready for this to not work, and take years and years of time and not be ready for flight. Well, about a month into the project, someone said, hey, someone just released an open source star tracker. Okay. And so we have a working star tracker about a year ahead of time, which is amazing. So this is called Open Star Tracker. We're building our own system for it, and actually we will probably be the first people to be running it. But with a little cell phone camera and a little computer that's this big, we'll be able to actually figure out which way the satellite is pointed by doing the star tracking. With a ridiculous amount of precision, which is really great. So we know which way we're pointed now, but if we're going to point down to the ground as we go over it and point at the Oregon high schools, how do we point the satellite? We could use little thrusters, but it turns out that requires fuel, and it turns out they don't like high-pressure fuel or things that catch fire in the International Space Station, so that's kind of out. So it turns out that if you remember your physics classes, the conservation of angular momentum saves your butt, because one thing that you can do is you can have powered fidget spinners. And when you take your fidget spinner and you start winding up that fidget spinner, it turns out there's a force that you don't notice on your hand going the opposite direction. Well, for us, the opposite direction makes the satellite go in the opposite direction. So we can control which way the satellite points using just motors. So this is a great demonstration of it. It's off the interwebs. So the only reason that's balancing are those wheels that you see turning. That's called a reaction wheel. And the person, you see how it speeds up when they press it? It's fighting that. So we tried it to see if we could do it ourselves. We have a drop tower at PSU. So that's our 1U CubeSat. And the fact that it stops right there meant that we could control the spinning of a satellite using reaction wheels. In fact, this is our thing that's now broken because we dropped it one too many times in the drop tower. And so, yay, we made reaction wheels. That was another thing that we thought was never going to work and now works, which is great. And then finally, there's one other problem that we have, which is that we want to not always have those reaction wheels spinning. They take power. So one of the things that you can do, which is really cool, is since the Earth has a magnetic field, if you make a magnetic field, you can fight it. So it's very hard to see, but what you're watching right there is a CubeSat suspended on a little bearing, and it's moving very, very slowly. It's using Earth's magnetic field. It's actually torquing against Earth's magnetic field. You can only do this 2 axes at a time, but this magnetorquer is how everybody in low Earth orbit actually points things, because it's kind of for free. and you don't have to spin your reaction wheels all the time. So you've got a satellite in orbit. Congratulations. It's got a radio, it's got power, it's got all the things. It's pointing and broadcasting to high school students. You're done, right? Oh, no. No, there's a lot left to do. And one of the things that you really need are ground stations, because you need to control the satellite, right? You have to upload new software. You have to make sure it's performing adequately, all the bugs you're going to find online. So how do you do that? Well, it turns out someone's already solved this problem for us, which is really great. It turns out that the LibreSpace Foundation has this project called SatNOGS, which is a terrible name, the Satellite Networked Open Ground Station. This, by the way, is a great community college and undergraduate project if you ever want to build one of these things. It is a ground station. It's receive only. It's part of a huge cloud-based network around the world. You can see this was a long time ago. There was about a dozen up. Now there's 2 or 3 dozen up all at the same time. You build one, you put it in your backyard, you connect it to the internet, and voila, you have a satellite ground station. And it's great. You can actually track satellites. You let other people track satellites. All the amateur radio CubeSats in orbit right now, of which there are several dozen, will then use your backyard ground station to download their data, which is really cool. It's a part of this big international project. One of the problems, though, is it's receive only, and we need to transmit to it. So we're building the big kid version of SatNOGS called the University Class Open Ground Station, which is another bad name. And that is transmit as well as receive. And so if SWOCC wanted its own ground station, they can go copy our ground station plans and transmit as well as receive to satellites. And we're actually hoping other universities and other community colleges do this because we desperately need more than just one ground station in Portland. Luckily enough, it looks like Hawaii is going to build one, and a university in South Africa is going to build one. And so the more people around the planet that do this, the more easy it will be to control our amateur satellites. There's problems with regulation and things like that, but we're working through those right now. It's called Uniclogs, and so we had to make an adorable mission patch for it. And yes, that is a helical antenna for a horn. All right, so you've got your ground station, you've got your satellite in orbit. What else do you need? Well, you got to test this thing. And in fact, NASA requires you to test it in certain ways. The first thing you have to do is shake it. And that means putting it in a vibration table and shaking the living hell out of it. Unfortunately, we've seen the results on YouTube. You can do some searches. I won't play them because they make me cry, of other CubeSats on a vibration table being shaken into little tiny bits. When you're in orbit, everything is serene and calm and great. But when you're going up on the rocket, especially if you're strapped to the bottom edge next to the engine, there's terrible vibrations for that 2 minutes that you're going up. So you strap it to a vibration table, and you throw it through a whole bunch of different vibrations and different G loads and all that kind of stuff. Tektronix up at Portland, Oregon is letting us use theirs, which is great because they cost a couple $1 million each. So shake and bake is the phrase that the NASA people use. The other thing we have to do besides shake it is we have to put it in a thermal vacuum chamber. What this does is 2 things. The first is it proves that our satellite will work when there's no convection to cool it. So we can do our thermal testing inside this thing. In fact, one things they do is they use liquid nitrogen on the walls to cool down the walls. And then you put a spotlight in from outside at 1.33 kilowatts per meter squared, which is about the sun. And so now you've got a really good thermal environment that mimics outer space. Part of baking it also is getting rid of all those volatile organic compounds, all that outgassing. You have to prove to NASA that when you're out in space, you're not going to start shedding things, including outgassing. And it turns out that PSU had a spare vacuum chamber, which was amazing. So thank you, Dr. Sanchez. We now have that. The other thing that we built ourselves was something called a Helmholtz Cage, which is 3 Helmholtz coils. If you see those orange parts, those are just coils of wire. In fact, this coil wire goes this way, and it turns out if you did your electromagnetics from physics, if you take 2 coils and power them in the same way, then it turns out right in between the 2 coils is a very well-known magnetic field. So we've got 3 sets of these coils, so we can make our own magnetic field, and now we can start to simulate being in orbit, right? Because if you just have your CubeSat there, you can do 1 degree of freedom against the Earth's magnetic field, but now we can do all 3 degrees of freedom and see how the satellite reacts. So now you're set. You know about satellites, you know about how to control them, how to build them, you know how to test them, you know about ground stations. So are we going to make it to space? Yeah, eventually. So it turns out we're almost done with the block diagram I showed you. There's still lots to do. But we are going to have a flat sat this winter, and that's where I take all these cards and I lay them on the table and put oscilloscopes and power supplies and kind of, you know, basically a big integration test platform. This summer, we're going to let NASA know that we're ready to go. And as soon as we do that, then we start sweating bullets because you can't say no to NASA. It turns out if you miss your flight, you're probably not going. So summer 2020 we'll deliver to NASA, and then fall 2020 they'll launch it to the International Space Station, deploy it from the ISS, and then 2020, 2021, oops, sorry about that, we'll actually be in space doing orbits and doing OreSat live passes and looking for cirrus clouds. After about a year in space, it turns out, remember at the beginning of the lecture I talked about space there's no really space there, the atmosphere keeps going. Well, it turns out that we're lucky. We're low enough in the orbit that we only have about a year. So in about a year, we're going to be Oregon's first meteor shower as well. OreSat will re-enter and burn up. We don't know where. We can't predict it. We hope over Oregon, of course. And will not be space junk. So that's good. So OreSat is very open. It's open source. And it's also open to all Oregonians. And we're hoping to have people come out and actually help us with this. There's lots to do. If you know people who do CNC machining, we desperately, desperately need their help. If you know anybody who has spherical air bearings sitting around, let us know. And of course, electrical test equipment and technical help. If you know people who are in technical fields that work with space and aerospace, we're looking for those people to help guide us as we build Oregon's first one. We don't have a lot of aerospace in Oregon. And of course, cold hard cash. It turns out that this is very expensive, and NASA's not paying for it, we are, so that's a lot of ramens, you know, from students to build this. We are looking for strategic partners. If you know people who want to support a huge STEM outreach for Oregon, please let me know. I'll have some contact information at the end. And also, we're hoping to get the ground stations actually sponsored to the high schools so the high school kids don't have to pay for them. It's only $50, but at the same time, we kind of hope that they don't have to pay for it. Thank you to the folks who are sponsoring us so far, including Alta Devices, who are giving us the solar cells since they've never flown in space, the Oregon Space Grant Consortium, and a bunch of open source space hipsters out there in the world. Thank you. And that's it. We have a website. Please hit it and sign yourself up for the mailing list if you're interested in seeing what's going on. We have a not very active Twitter account, but that does so far tell you what's going on with us. And there's my contact information if you want more technical detail. Thank you for listening, and I'm happy to answer questions, and also happy to have people come up and take a look at some of the show and tell that I brought tonight. Any questions? Oh, go ahead. Right, that's a really good question, actually. It turns out that, you know, you've seen a lot of really unhappy people talk about space junk because space junk really is a problem. It turns out it's not that much of a problem. Especially for something teeny tiny like this, the odds of something hitting it are astronomically small because space is huge. When you start to have people in space, you start to get very, very, very worried because even a small thing will take out people. But if a bit of space junk hit this, it would probably destroy it, but the odds of that are hundreds of millions to one. So that probably won't kill us. What will probably kill us is the bad software my undergraduate students are writing. That's much more likely. But luckily enough, in space, it's not that bad right now. It may be worse in the future, but there's really great stuff going on in the international community right now about making sure space junk is being taken care of. We've got satellites up there that are doing the first prototypes of capturing it and getting rid of it. And also, you can't send space junk up anymore. You've got to have what's called an orbital debris mitigation plan. And so the international community is already starting to rally around, hey, you can't pollute up here because it's going to kill someone. Ooh, can we tap, the question is, can we tap in to previous satellite makers and not reinvent the wheel? Kind of is the answer. And you must be a plant. I don't know you, but that was like the best question ever. Thank you. In the sense that, why are we making an open source satellite, right? And the answer is exactly that reason. We don't want to, so you can buy a satellite, a CubeSat, off the shelf. It's only going to cost you $200,000. Maybe another 5 years, it'll only be $100,000. But undergraduate students are free, and we've got lots and lots of them, and they love building stuff. So can't we just have them build us a satellite? Well, it turns out no, because there are not plans for these things online. There's plenty of textbooks about reaction wheels or magnetorquers or all this stuff, and the textbooks are great, but there's no designs. And so UPSat that I mentioned earlier and OreSat will be the first of the truly open source designs where people can literally build it themselves for probably under $10,000 and have a working CubeSat. And so no, we're doing a lot of the pioneering ourselves because we're so annoyed that we have to do it ourselves that we're doing it ourselves. And hopefully we won't have to do this. Again, hopefully in the open source spirit, other groups will come, look at our stuff, laugh because it's so terrible, and improve it. So when we do OreSat 2, which is a mission to Jupiter in a 6U CubeSat, wish us luck, then all of these systems will be improved by the time we do that. So. Yeah. Thank you. Yeah, so Celestron, yes, it was really exciting. The Celestron star trackers were the reason we thought we might be able to do it ourselves. And it turned out to be easier than we thought, which is maybe one reason why you can buy these things now. But it's really cool. Oh, and I forgot to show this. This is actually one of our cameras. It's kind of difficult to see, but the funny shine thing in the very middle is the camera. The other question was, thank you, the resolution of the cameras. So this camera is 1080p, so it's 1920 by 1080. It's 30 frames per second. It is a crappy cell phone-like camera, but they're super cheap. They're about 20 bucks each. By the time we get into orbit, we'll have something like 100 meters per pixel. So we are not doing anything spy satellite. We will not be reading license plates, but we will see large chunks of the ground. And so it's good enough to see cirrus clouds, and it's good enough to probably pick maybe your school up as a single pixel, but that's about it. Right, so that's something you have to worry about is you have to vet all the open source stuff that you use yourself, right? Yeah, and this is a problem in like Linux and other open source projects, right? You have to be very careful about what you do. That would be another lecture on open source security. But we do things to make sure that what we have is what we think we have. And there's code reviews, and there's testing, and there's all sorts of things like that. But that is one of the problems when you start letting other people in on your open source project. You have to be a little careful. And actually, it's 99.999. I've actually not seen, I've only seen a couple cases of malicious coding, but about 100% of it is just bugs, is people who don't know what they're doing writing open source software and making open source things, much like us. There are warnings on all of our repositories with each, the star tracker and the GPS system and the reaction wheels. And the warning is, this has not flown, do not use this, right? So yeah, it's an issue. Yeah, we do. He was talking about coronal mass ejections and things that make us not sleep at night. Way back here, sorry, I don't know what the home button is. No, keep going. That. The answer is, it doesn't matter that we're small for radiation. We're going to get hit. And if there's a huge coronal mass ejection or if there's a huge space weather phenomenon, we will be affected. Luckily, again, we're under the Van Allen belts, so the geosynchronous ones that are outside the Van Allen belts, they will get toasted because they're not protected by them. So we have a much better chance. The other thing that we have a better chance of is that we have lots of little redundant systems. And this idea down below, this defensive design, we can't afford radiation-tolerant processors. They're like I think they're only $1,000 each now, as opposed to $150 from DigiKey, right? But if we have enough of these in parallel, and especially the really critical ones for the satellite, then we can power down the satellite, power it back up, and then compare the output from these two different computers talking to each other, these two chips. So we're trying to do all of the defensive design that we can possibly do using commercial off-the-shelf parts. It turns out there is one radiation-tolerant part on this, and it's a watchdog timer. And so even when our redundant system locks up and catches fire, that one radiation-tolerant part will actually power cycle the whole satellite. And again, one of the things that I won't go into, but power cycling the satellite, bring all of the power down, turns out to be the right way to deal with about 80% of the problems in space. Single event burnouts, when they actually start burning out transistors in your circuit, there's not much you can do about that. So. Yeah. Yeah, it's Oregon's first satellite, so yes, we would like to. We are absolutely happy to go out of state for anybody who's willing to give us stuff. So like Alta Devices is California, and we will happily fly their solar cells. We'd like to keep as much of it within Oregon as possible, but we don't really care. Right. But part of OreSat, we hope, is some of these high schools and also community colleges that have these kinds of things getting involved and working on things. One of the problems is we need it, what's the right way to say this? It's got to be done right, unfortunately, and it's pretty high precision. It's not terribly high precision. Any commercial place could probably do it. It's only a couple of thousandths of an inch, or a couple hundred micrometers, but it's got to be done right, otherwise it won't fit. But we would love technical partners like high schools even, or community colleges that are willing to do that kind of precision. And in fact, all the stuff is posted. It's something they could start right away. Thank you. Yeah. So it's ancient Wi-Fi, it turns out. It's 802.11b, and we did that because of the power amplifier that we're building ourselves. Go back to that page. And so 802.11b turns out to be only 2 megabits per second. We hope to get all 2 megabits per second, but we won't. There'll be dropouts, there'll be noise, there'll be bit flips, all that sort of stuff. And so we're probably in the 1 to slightly less than 1 megabit per second using Wi-Fi. And we could use the real fancy, 100 megabit per second 802.11n's and other newer Wi-Fis. The problem is that they're not meant for long distance communication. And 802.11b, the old one, turns out to be hackable, abusable, whatever words you want to use to make it into a good transmit-only radio. Any other questions? Go ahead. Oh, gallium arsenic, yeah. So solar cells that you see around Oregon, they're almost all silicon solar cells. They're made out of silicon. This solar cell is made using gallium and arsenide. Arsenic, what is arsenide? It's arsenic and oxygen? Actually, I don't know. That's embarrassing. Anyway, it's essentially, it's gallium doped with arsenic. No. Gallium arsenide is the actual crystal lattice that we're using, as far as I know. It's a crystal, right? Yeah, okay, so it's a crystal substrate. Instead of silicon, we use gallium and arsenic. And that is very, very thin. It's not toxic, even though it's got arsenic in it. It's its own crystal. The ones that we're using, you can see, are actually flexible, which is really cool. And they're really high efficiency. The silicon ones you see around here are like 15% efficient. Ours are twice as much at 30%. Yeah. Yeah, they're just that thin. That funny CVD, the chemical vapor deposition, they're just taking the gallium and the arsenic and vaporizing it and letting it settle in this very, very, very thin film. Yeah. Any other questions? Right, right. We're actually excited to run this one. All right. Well, thank you guys. I'll be up if you've got more questions. I'll answer it and come take a look and grab our first prototype and take a look at it. Thanks, guys.